Maths educational video, polar coordinates. In this video, we're going to learn a new way of representing points on the xy plane. The usual way is to specify x and y coordinates. Now we'd like to change this pair of numbers to a new pair of numbers, r theta, which I'll define now. R is simply the distance between O and the point P. Theta is related to this angle alpha, which is the angle between the positive x-axis and the line segment OP. So alpha will always be positive because it measures the size of an angle. But now we like to differentiate between points above the x-axis and those below. So we define theta to be exactly alpha if the point lies either on the x-axis or above it. So y more than equals 0. And for those points below, strictly below the x-axis, theta will be taken to be negative alpha. So this new pair of numbers, r theta, will be known as the polar coordinates of the point P. Apparently, there are some special cases we have to address. The first is the origin itself. Based on the definition of r will be 0 for origin because r measures the distance from the point to the origin. So obviously at the origin itself, distance is 0. Actually, theta can take any value. But for simplicity and for uniqueness, we will take it to be 0 for r and 0 for theta. Another special case is the positive x-axis. Obviously, theta is 0 based on the definition of theta. And as for points on the negative x-axis, again, based on the definition of theta, the angle between the green line, any point on the green line, and the positive x-axis will be pi. There are some more jargons to learn. In the polar coordinate system, the origin is sometimes known as the pole. The positive x-axis is called the polar axis. And as we already know, r theta will be known as the polar coordinates of the point P. A quick example, let's take the point with rectangular or Cartesian coordinates, -1, -1. Our job is to convert this to r theta. Based on the definition, r is the distance from O to P. Obviously, it is using Pythagoras theorem, square root of 2. As for theta, we first compute alpha, which is the angle between the positive x-axis and the line segment OP. It turns out to be 135 degrees, or -3 pi over 4. But because this point lies below the x-axis, theta is negative of alpha. Therefore, this point P has polar coordinates square root 2 for r, -3 pi over 4 for theta. Just two quick remarks about polar coordinates. The first is that r theta and r theta plus 2m pi represent the same point. This is obvious because theta plus 2m pi means you rotate this line segment OP through n complete revolution. Through one revolution, you add 2 pi to the angle. So 2m pi means n complete rounds. But doing so results in the same point. But for uniqueness, we will just take r theta, where theta lies between -pi and pi. Because we do not want to have two or more r polar coordinates representing the same point. It's also possible to allow r to be negative. Now here is just a specification for your interest. But we will not consider the case when r is negative, because that is absolutely unnecessary. So for subsequent discussion, we will take r to be positive. So this is just for your interest. So far we have been talking about converting a point in the usual Cartesian or xy coordinates to polar coordinates. If we need to do the other way around, here's the formula. From r theta to xy, you use this pair of formulas. X is r cosine theta, y is r sine theta. A quick example, if you are asked to convert this point 5 minus pi over 6 in polar form to Cartesian coordinates, meaning xy, you just apply the formula. Polar curves. It's possible to specify a curve in terms of a polar equation, either explicitly r equals to f of theta for some function f, or sometimes implicitly. Then the graph of this polar equation is made up of all the points satisfying the equation. We'll look at two important examples. In the first example, the function is a constant a, positive. How do we sketch this graph? It turns out to be very easy because r measures the distance from the point to the origin. And now we have a constant distance, so obviously it must be a circle, because any point in the circle has a constant distance of the radius from the origin. So remember this, r equals to a constant, has a graph which is a circle centered at the origin, and a radius of a. Example 2 is more complicated. R is a cosine theta. We apply a special trick. We multiply both sides of the equation by r. The reason for doing so is obvious. Now we get r squared, which can be converted to x squared plus y squared. And on the right hand side, r cosine theta will be replaced with x, based on the first equation that you see in the box. So now we have something involving x and y only. So this is called the Cartesian equation, which is what we need. But in order to know what this equation represents, we complete the squares. In this case for x. So what you need to do is bring the term ax over to the left hand side and do what is known as completing the squares. So now you get something we are familiar with. This is the equation of a circle centered at a over 2, 0, and the radius will be the square root of the constant term here, which is a over 2. We end the video with what is known as polar rectangles. This will be useful for the double integral that we're going to do in a separate video. The polar rectangle is actually a region bounded within a concentric circle here, so is for region satisfying two inequalities, r between a and b. Now we understand from the previous example that r equals to a constant represents a circle. So when r lies between two constants, the region will be between two circles, which is a region in gray. For the second inequality, theta between alpha and beta tells us that it's not the entire concentric circle, but only those between these two dotted lines, which specifies the angle. Theta equals alpha and theta equals to beta. So the region in gray is known as a polar rectangle. A special case of a polar rectangle is when a is 0. So back to this diagram, if a equals to 0, then this portion in white will disappear. And what we get will be a sector of a circle with radius b.